Looks like we're live. Hello everyone and welcome to yet another Azuzin session. So let's make a little bit of announcement and officially start the stream. So there we go. Discord as usual. Also Discord on old laptop. This is how it works on an old laptop from which I'm also trying to stream. So yeah, it needs to load everything up. It needs to recalculate the layout. Finally, it managed to do that. I'm really happy. Okay, so let's do the usual red circle live on Twitch. And what are we doing today? We continue developing the rope long enough to shoot our leg. Right, so I'm gonna give the link to the Twitch TV/Soding. I don't know how to type Soding, and I'm gonna ping everyone who's interested in being pinged. And there we go. So for those who don't know, maybe there is some of you who are too young. There is a such book, a rope long enough to shoot your leg. Right. So enough rope to shoot yourself in the foot. It's actually, oh, it's a foot, not leg. But I mean, I'm a filthy Slav, so I don't know the difference between leg and foot, and in fact, I don't understand why English speakers like actually distinguish them. Anyway, so yeah, it's basically the book about the different pitfalls of C and C++, right? So that's basically the reference. Maybe I should actually like fix leg. I'm gonna just quickly replace leg with foot. There we go. Alright, so today we're gonna continue developing the thing that we started to develop on the previous stream, and basically the rope simulation in Giant, which is inspired by day 9 of Advent of Code. So, and I just wanted to add a couple of features that I mentioned in the previous stream, and that's gonna be basically it for this project, right? So let me see. So do we have anything to fetch or maybe to commit? So let me see. I think I didn't work on this off screen. Right. And there we go. So if we run this entire thing, right, so this is how it looks like. And basically you have a rope that acts like a rope almost, right? So it has some sort of elasticity and stuff like that. And we actually lost it because the only node that we can drag around is the red one, right? And that's one of the things I wanted to add to this simulation, right? So essentially I want to be able to drag any node, right? But the reason why I cannot do that right now is because the velocities of all of the consecutive nodes are calculated starting from the head. So we take the head as the base position, then we recalculate the velocities for the one before the head, and then for the one before the head, like in based on this one, and then this one based on this one, and so on and so forth. So basically the changes are propagated from head to the tail. If we want to be able to actually drag anything, we need to learn how to propagate changes in both of the directions. Right, we already discussed how we can do that. We can basically see, we can basically compute the velocities considering this ahead for this one or this ahead for this one, and then just take the sum of them. Right, and it will sort of maybe make it work. And another thing I wanted to actually do, I wanted to add an ability to branch out, right? As you can see, each node can have two neighboring nodes maximum, right? So what if we add an ability to like build, you know, something like trees, right? Or maybe even graphs, who knows? Maybe we can build the graphs, and maybe you can even build like elastic structures out of that. So that's gonna be actually kind of interesting. So yeah. But the first thing we're gonna probably implement, I'm gonna implement something pretty much technical, right? Because there is a problem, is that this thing only works for very specific resolution. And if I accidentally resize the window, I can't grab anything anymore. As you can see, I can't click on it. And this is because all of the mouse positions are calculated relative to the previous size of the window. So this is something that I forgot to sort of change in the previous stream. And this is something that we're going to do probably right now. So to do that, we probably need to handle window resize events, right? And as far as I know, we can actually find the window resize example somewhere in the modules, right? So let's actually go to OPT, Giant. But by the way, if you want to have the source code for this entire thing, I'm going to copy paste it in the chat. I think I didn't copy paste it in the chat, so now it's now in the chat. And for people who's watching on YouTube, I'm going to put that in the description as well. So there we go. Now, let me see, what is it called? It's called rope J. There we go, it's called rope J. And now, I'm going to just go to OPT J, modules, simp, examples. Or maybe it shouldn't be in the simp actually, because we have to look into the window creation, right? So it's basically window creation, example, window creation. Do we have anything related to resize? No, we don't really have anything related to resize, so probably have to go to the simp then. Do we have anything related to resize? Yeah, there we go. Okay, so in the event loop, we update all of the events and then we get window resizes. Right, and then we iterate through all of them. So I suppose you can have several window resizes and you sort of handle each individual of them. Which is rather interesting. So we can just take a look at what exactly update actually like window resizes do. Simp will do nothing if it doesn't care about this window. Simp will do nothing if it doesn't care about this window. Huh, maybe this is needed if you have several windows. Right, but we probably have to take a look at both of these things, right? So what is the get window resizes and what is update window and so on and so forth. But maybe update window is just like cleaning it up, who knows? All right, so let's actually go to the input and let's just grab this specific thing. Right, somehow lost my clipboard. And somehow lost my clipboard. Okay, so and the thing I want to actually find in here is this one, get window resizes, and essentially it's array of structures, and each structure basically has the width and height and the window type, and I have no idea what is a window type. It's located in a separate module, sure. I think it can work with that. Window type, and what kind of windows we... Oh, okay. I thought it's sort of like enumeration, right? You know, usually people have some sort of entities and enumeration that describes the type of that entity. I thought it's one of those things. But apparently it's a platform-specific type, right? So on Windows it's handler, the window handler. On Linux it's the X11 window thingy. And on macOS, whatever you have on macOS, weird Objective-C thingy that I never understood and probably will never actually learn, right? Because the only language the only place where you need Objective-C is you know, Apple stuff, and I don't have any money for Apple stuff and actually any opportunity to even buy Apple stuff, so I'll never even understand like this alien stuff, and I'm not really sure if I care. Okay, so this is what it means. So essentially it's not really a window type, it's like specifically the window that got updated. Okay, cool. So let me take a look at the other thing. So we also call update window, and I'm really curious what is update window and why do we have to call it? What it's all about? What is this thing all about? Let's find out. So doesn't really explain what it is. Ignore window if we don't understand. It's kind of interesting. It's kind of related to what it actually said in here. Simp will do nothing if it doesn't care about this window, and then within this function, ignore window we don't understand. Right? It's kind of funny, right? So in the place where we call this function, we say simp will just ignore it. In the function itself, we say, well, I will ignore it if I don't understand what it is. It's like two places of code communicate with each other. It's kind of funny. Also, I forgot to put something behind my camera so I can know precisely what you can or cannot see. Sometimes I forget to do that. Sometimes I forget to do that. So I'm not really sure what this function does, right? So you see, that's the problem. Do we really need to call this update window? Maybe we should, right? So maybe I should just like just call it anyway. I don't see any problem with that, to be fair. I don't see any problem. So let's go to the rope.js and just port this code there. Just port this code there. So let me find not quit. So in here we just update all of the window events. After we updated all of the window events, we iterate through all the window resizes, right? And in here we just update the window. Update the window. And most importantly, we probably need to remember the new size of the window, right? So that's what's important. So as you can see, we compute the mouse position relative to window height, which is effectively hard-coded, right? It's a constant that is hard-coded. Right, and when we resize the window, we have to actually update this entire thing. So that means this kind of stuff has to be an variable, right? It must be a variable. So, okay, we can keep this thing in here, and we can create a global variable, like a window width, right? So initially it is going to be the constant window width, right? But throughout the execution of the program, it's going to change, of course, right? So this is going to be height, and this is going to be height as well. All right. So when we create the window, we're going to use the variable version in here. All right. So let's actually use the variable version. So here we are initializing everything with the variable version. This is also going to be the variable version. Okay. So window width. All right. So and when we update this entire thing, we're going to just do window width equal it width, right? And then here we can just do height. There we go. So mouse pointer something something. So and in here we're gonna just do that. So essentially when we resize, this variable is going to be updated, so everything here is going to be updated as well, right? So that's basically the entire fix, essentially, right? If I didn't miss anything, right? So let me just do that. I'm gonna recompile the stuff. It does not recompile because why? Procedure call did not match any possible overloads. It wanted to have... Ooh, this is very interesting. So it wants to have float, but this thing is an integer. But when I use the constant, it actually worked fine. That is very interesting. So when I use the constant, it was not inferred to be an integer. So maybe it has some sort of abstract number type that is basically converted depending on what you need in this specific case. But anyway, I can always just say, all right, implicitly convert that to whatever type you want. So that's basically what XX means. And that didn't really work well. So, okay. Can I just, just wrap this entire thing around and just like just convert it to whatever? Yeah, that's what I wanted. That's everything I wanted. Thank you so much. Thank you so much. I really appreciate that. Okay, so cool. We can drag it around, but if I resize this mother flipper, can I still drag it? I still can drag it around because the remembered width and height of the window was updated, so I can do this kind of shit with any size of the window. I can actually resize and everything should be working properly. This is like a small thing that I wanted to fix on the previous stream, but I completely forgot about that. I think it's quite important to have it fixed. So, and let's actually do a committee and maybe even push and move on to actual things that we wanted to implement today. Okay. Fix broken dragging on window resize, right? So I'm gonna push that right into the repo, and there you go. Wasn't that epic? I think that was pretty freaking epic. Okay, so what did we want to do? We wanted to actually be able to drag around any nodes, right? So let's just go ahead and see how we can do that. All right, so essentially right now we are checking whether we're close enough to the head, right? So if you press mouse button down, we just look at the current mouse position and we check if it's close enough to the head, Right. So now, if we want to actually be able to drag any of these nodes, we need to check it against all of the segments of the tail, right? And if we hit any of the segments of the tail, we have to remember which segment we hit, right? Which segment we hit, and then drag around that specific segment. So as you can see here, we just set the drag to true, and the drag, if it's true, we just set the head to mouse position. Right, so that means we need to actually keep track of what exactly we hit in there. Okay. So for that, I might actually introduce temporarily enumeration, right? So let me see, let's call it not. Right, not type. And this is enumeration, right? So this is enumeration, and you can have a head in here or a tail, right? And tail, head is going to be 0 and tail is going to be 1, but tail also essentially, so it's going to be sort of a trick, right? It's going to be sort of a trick. So drag not, right? And initially it's going to be head, right? So if the drag not is equal to head, that means you're dragging the head. If the drag not is greater or equal than tail, that means you're dragging one of the tail. And which of the segments of the tail you're dragging? Well, you're dragging drag not minus tail, right? So essentially we're also storing the index of the tail that we're dragging in there, right? So, which actually brings us to the idea that probably the head has to be part of the tail, right, to make it easier, because that eliminates the enumeration and stuff like that, and that makes more sense. But that makes more sense in a context if you can drag any node. Remember, we haven't implemented that yet, so that means before we were only dragging the head, and in the context of dragging only the head, it makes sense to keep the head separate from the tail. You see? So it's kind of like, depending on how you change the assumptions, how you change the technical requirements, some of the code that you had before may look kind of stupid, but it's not stupid if you have certain assumptions. You know what I mean? Right. So we can say, well, obviously had to be part of the tail. No. It's not that obvious, right? If your technical requirement to drag only the head, it makes a lot of sense, and it's actually easier to handle it like that. You know what I mean? Maybe not. So maybe you can also make the head part of this entire thing. It's just like you, instead of referring to the head, you always refer to the tail 0. Anyway, so let's not rat hole on that too much, so let's just implement something that is actually working. I think, yeah, I think that's more important. Anyway, so let's go. If we're close enough to the head, we're gonna say, okay, drag is equal to true, right? And drag not is equal to the head. Okay, cool. So otherwise, we need to check the rest of the tails, right? So let's actually do something like this. It's going to be tail. Let's iterate through all of the tails, and also here let's take the length between the mouse position and the current tail, right? The current tail, and if it's less than the node radii, so we're also going to set the drag to true. And the drag node is going to be tail. And I think there was a way to actually take the index of the current thingy. I think it's like it index, right? It refers to the current element that you're iterating, and it index refers to the index of that element. All right, so we can actually work like that. Okay, if we are dragging, right? So if we are dragging, we have to check what exactly we're dragging. Drag not. Right, so what is the node that we're currently dragging? So if we're dragging the head, right, so we're gonna just say, okay, head equal to the mouse position. If it's otherwise, oh, this one is very complicated. You just can't do that because it can be greater, right? So because of that, it kind of makes sense to maybe check if it's greater or equal than tail. only then just do tail drag not minus tail, right, equal the mouse position. Right, something like that. So that's what we want to be able to do. There we go. Something like this, right? So, and let's actually go ahead and go through the compilation errors, because this entire thing probably not gonna compile. Right, so what do we have in here? Oh yeah, okay, so it cannot infer this specific type. There's not enough information to infer this type, so we have to say not type dot head. Okay. What else do we have? Type mismatch in here. Okay, this one is rather interesting. Can I actually cast to like this thing to not type, or do I have to do some other shit? Okay, I managed to do that. That's kind of interesting. So you can actually, you automatically have a plus for enumerations. Makes sense, I guess. Kind of cool. Alrighty, so let's go ahead and see how it works. I actually want to reduce the amount of segments of the tail, because I think 20 is too much. Right, so let's actually make 10 of them, so it's a little bit more manageable. Okay, so what do we have? So here's the head. I can drag around the head, and I'm gonna try to drag around one of the tails, and I'm gonna show you what exactly is the problem. As you can see, it doesn't work. Well, it kind of does work. But it always snaps back to this thing. So the rest of the rope doesn't follow this one, because it's coded so this thing always follows this thing. It cannot go in the opposite direction. Only by dragging this thing you can make them all follow the initial head. But if you drag any of these things, they always try to follow the one that is ahead of them. So that's one of the problems that prevents us from doing this kind of thing. And we just need to code this entire stuff slightly differently. Alright, so let's actually see how exactly we can code all of that. So essentially, before we fix the problem, I think the time has come to get rid of the head and just make it like a single universal rope, right? Essentially, just straight up get rid of the head, right? Just get rid of the head, and the head should be now a tail 0, right? Just make it tail 0. So the way we're gonna do that, I'm gonna just simply remove the head and remove the not type, right? And it's going to fail in all of the places, where it was used, and we're gonna follow and fix all of these places, and we're going to yeah, it's basically going to be compiled. So let's actually go through the compilation errors and see what we have, right? So now I suppose this thing has to be just an index, right? So I can just make it 0 for now, right? So we'll just make it 0. So we don't have a head anymore, so that means none of that really matters, right? So we iterate through each individual segment of the tail. If it's close enough, if this entire thing is close enough, we just do that. But now we can just like simply use the current index, index. Since we don't really have this separation between the head and the tail, maybe we can just have a single drag, which is an integer, and if it's negative, that means we're not dragging, right? And if it's you know, non-negative, 0 or greater than 0, so that means we're dragging the corresponding index. So this is one of the things we can do. So let me just put -1 in here, right? So it's gonna be -1, and I simply can just do drag, I'm pretty sure. So, and when I unpress this entire thing, this is just a -1. Right. So you drag a node in the middle, does it ever behave as there are two ropes that share a head? No. Or you mentioned something about averaging the neighbors. Yes, I mentioned something about averaging the neighbors, and this is because we need to implement that. We do not average between the neighbors, and that's what we implemented right now. Right, so we are in the middle of making it work properly. right? So it doesn't work properly right now. We're in the middle of implementing it so it works properly. Okay, so we don't need this thing anymore, right? So we can only use the drag, and in here, if this thing is greater or equal than 0, that means we can just set this thing to the mouse position, and that should be basically it, except we also need to get rid of all of that stuff, right? There we go. So we don't have a head, so we just recompute the velocity in here, so essentially I can just do it like that. Interestingly, I don't really need to recompute the velocity of this thing for now. I see what's going on. So what I have to do, I actually have to do 0, 2, alright, and I just have to, yeah, so I have to just like swap it around. So now it is like that. Alright, okay. So, and after that we are updating this thing, and I'm not quite sure, maybe I could merge these two loops, but maybe it doesn't really matter, so I'm gonna just keep it like this. Okay, so here we just draw the line, right? We just draw the line, but essentially I have to do a similar thing in here. I have to do -2 and just like +1 in here. Right, and after that, the only thing I have to do, so maybe now I can just simply get rid of the circles, so we're not gonna have the red circles anymore. Right, we're not gonna have any red circles anymore, so that should be fine. So, okay, so everything seems to be compiling, so let me see if it didn't break. It freaking exploded. Okay, so the rope freaking exploded, right? So, you know, it's one of those ropes. Some ropes are long enough to actually shoot your foot. This rope is long enough to explode your entire fucking leg. So that's what it is. All right, so let me see, like, what exactly happened. That's so weird. So maybe exploding rope seems more fun. Yeah, so it just explodes, and it actually goes away so hard that it disappears at some point. So I'm pretty sure I know what's going on here, so I just need to go through this entire stuff. So drag is initially -1, right? If we're close enough to this entire thing, we just set it to the index. And maybe we also have to like break out of the index. I don't know why I didn't think about breaking out of the index. So let's just break out of it. So if this thing is greater or equal than 0, that means we just constantly set its position to that. So the next thing, we need to recompute the velocities of this stuff, right? So, and when we're computing the velocity, right, so compute tail velocity, so we assume the first argument to be the head and then the tail. Okay, so yeah, and that gives us the velocity of this specific thing that we're computing. I see. So it still has to be something like this, right? It still has to be something like this, with +1, this one, and then +1 in here, right? If we want to recompute the velocity. So let me double check with this thing. So it has to be +1 because now it is like, okay, I see. All right, so that makes sense. So now here we are updating the velocity also of these things. Then we're drawing basically the thick line between all of these things, and then we draw the circle between those things. Okay, so that should kind of fix it. So let me now try to run this entire thing, and boom, it actually exploded, but now in terms of memory. Okay, so where exactly that failed? Okay, it's 1 1 1. 1 1. Well, I mean, yeah, I suppose that's how it has to be done. And let me double check. I think it has to be like -1, but it, right? Because now, or we're computing the current velocity, but we're doing, yeah, that's what we have to do, right? Isn't it? Yeah, that's what we have to do. Yeah, there we go. So we're computing this entire shit except for the last one, right? Okay, that's cool. And then, let me see. Okay, so that's cool. So everything seems to be working. So we finally get rid of that nasty head, right? So now everything is uniform, and I can go ahead and rename the array tail to rope, right? Not reaper, rope. I mean, it's almost the same. It's just so you swap O and E, and you basically get the rope. So in here, I can just replace. Yeah, I think I could have just like query replace tail with rope, and just a boom, and there we go, and that should just work. No, except compute. I think it should be called node velocity, right? So tail velocity. Node velocity. Okay, cool. So seems to be working, seems to be at working. That's pretty cool. So we can do that, and there we go, there we go. Cool. So how do we want to do that? We want to essentially here accept not the node for which we're computing the new velocity, and the node that affect the current node. You know what I mean? Right. So, and we can have like up to 2 of such nodes that affect the current one. So, and I'm thinking, how do we even want to do that? Right. So we need a function that accepts like the current node and its neighbors, right? Its neighbors, and I want it to be like an array of them, because I'm gonna in the future I'm gonna actually make like not only the rope, but it's gonna be sort of like a graph, right? So, and because of that, we need to be able to just handle the neighbors like somehow. Like we need to be able to provide several neighbors. You know what's interesting? We're programming in an actually good language with variadics and shit. Why can't we make this thing variadic? For instance, if you are on the edges, right, we're gonna only provide the like one neighbor. If you're in the middle of the row, we're gonna provide 2 neighbors, right? So we're not programming in C where variadics are painful. We're programming in a modern, like, proper language. But I don't remember how to use variadics in here, so I probably have to search for the module and stuff. So let me see. So this is gonna be print. I know only one variadic function, which is print. It's probably located in basics, so let's actually reduce the grab times by searching in here. And there we go. Oh yeah, this is how we do that. So essentially you just put dot in here, and there you go. This is something interesting. I think I already mentioned that before, but this is something very unique to this language that I didn't see in any other languages. You can have other arguments after the variadic, which is kind of like weird, because usually I tried a lot of different languages, right? And all of the languages, they just like, yeah, okay, so we're gonna put variadics only at the end, and if you're gonna put something after, you're not allowed. You can only put variadics after that. You can put variadics in the middle, like, fuck it, sure, you can put them in the middle, and the compiler actually goes through the effort to understand whether you provided the arguments correctly in here. So it's so cool, actually. That's pretty cool. And I suppose it's also the fact that you can explicitly provide the names of the argument makes it a little bit easier to use as well, right? Because at any point you can just like call print, just do some stuff in here and just directly say I want to assign toStandard error to true, right? So it makes it actually easier, but I don't know. I think it's kind of cool. Anyway, so yeah, I just want you to have some examples on how to do that. So main, where is my main? I think I lost. Okay. So okay. So neighbors, I already forgot neighbors. So we're gonna just have something like this in here. So, and this thing should return the velocity. Okay. Surprisingly, I think it will just work, right? I think it will kind of work, but not really. I ran out of water, so I think I'll need to make a small break, right? So because I want to refill my tea. But first I'm gonna actually finish this function. So we are computing the velocity. So here is very interesting thing. So we're computing the velocity specifically for tail in here, right? But for this function, we're gonna be computing velocity specifically for the head, right? So let's actually not call it head. Let's actually call it knot, right? So we're gonna have pretty much the same elasticity in here, right? And what we want to do, we want to iterate through the neighbors, right? So let's go ahead and iterate through the neighbors. And let's find the length between the... it's a little bit mind-bending because we're computing this for the tail, but now we're computing it for the knot, right? And the head is the neighbor. So I have to make a mental substitution for this specific code. I need to replace tail with knot, right? And head with it, right? So that's what I have to do. So I have to have like a mental substitution in here. Not really mental, I can actually directly just substitute with my text editor, right? So let's go ahead and query replace tail with knot. So because that's for what we're computing this entire thing. And the head, we're going to replace it with it, right? There we go. And the target, right? So, and this is basically the velocity, right? So this is the velocity that is affecting the current thing. So interestingly, I can create a vector. I can create a vector. That is going to be the resulting vector, right? So this is going to be make vector 2, which is initially going to be 0. And what we're going to be doing, we're going to be basically adding these neighboring vectors. We're going to sum them up. So this is going to be just like a sum of those things, right? So and then we're going to just return the result in here. So for this thing, I'm going to just like back it up, right? I'm going to just back it up. And we need to start using this new thing, right? So let me go ahead and just like recompile everything, just to make sure that you know, it still works. It doesn't really work because did I accidentally remove this entire thing? Yeah, I think I did it. Okay, I'm sorry. Make vector 2 0. All right, so there we go. Wait, how did that happen? Didn't I? Okay. I thought when I was replacing, I actually didn't replace it for this specific thing. Yeah, that makes sense. Thank you so much, Fast Magic 47. Hope you're doing well, good sir. No, I'm definitely not doing good. But thank you so much for this stuff. I really appreciate that. I'm slowly going insane. All right. So let me see. So what we need to do in here. I suppose we're going to be just iterating through all of the ropes, right? We're going to be iterating through all of the ropes. And if it is greater than, if it's equal to 0, let's put it this way, right? So we're going to be doing something like this. We're going to compute velocity for this specific thing, but the only neighbor that we're going to have and it plus 1 is less than rope count, we're gonna do rope. You know, I don't know. Maybe it would be nice to actually have this kind of stuff before, if you know what I mean. Alright, so essentially 0 is just 0, 1, right? It's just 0, 1. But it only makes sense if you have more than one segment. So rope count has to be greater than 1. Only then this entire stuff makes sense, right? Only then it makes sense to even recompute anything in here, right? And then we're starting to iterate from 1, right? So from 1, but also 1 before the count. So and that way we essentially computing it for it minus 1 and rope it plus 1, right? There we go. So something like this. So these are the neighbors in here. And then we're gonna compute the last thing, which is the rope count. Actually, we have something like, don't we have like a rope? Yeah. Instead of using rope count, I think we have to use rope length, right? Because we have two parallel arrays. Right. So because of that, I think we need to replace rope count with rope length. Yeah. So because we have two arrays with the same length, so to say that we're sort of indexing both of them, let's actually use this specific constant. I think that's pretty cool. So minus 1, and we're only computing this thing for rope length minus 1 and rope length minus 2, and that should work out because this thing is greater than 1, so that means it's at least 2. So that means you will be able to actually like subtract 2 in here, so that should be fine. There we go. So as you can see, since this thing is like sort of variadic, we can provide 2 neighbors or we can provide 1 neighbor depending on what we want to have in here. And in the future, if we're gonna have like several neighbors, maybe it will work out as well. But maybe if we're gonna start like doing like a graph out of the nodes, we're gonna just represent the rope slightly differently, right? We're probably gonna have an array of nodes, right, and then a separate array of connections between them, right? In that particular case, the function that computes the velocity, they're probably gonna consult or query the data structure with connections directly. There we go. All right, so it seems to be compiling. So, and now, if we try to do this entire thing, so, okay, okay, I can drag on this thing. Can I drag on the... Okay. So it works kind of in both of the directions. So yeah. Pretty cool. so now you can... Well, I mean, it's a little bit stiff to be fair, but... That's kind of cool. I suppose we can just change some of the parameters. So yeah, so if we set elasticity, well, it's not very elasticity. So the greater this thing is, the more sort of like rigid, more stiff it is. So maybe I would actually rename elasticity to something like stiffness. I think that's what it is. Right. So we actually need to remove this function. Could we replace? Yeah, it's more of a stiffness. So, and on top of that, let's do Linux main. Okay, so what do we have in here? So it's a bit, it should be a bit more stiff now if I increase it to 30. You don't really want to make it too big because it starts to act kind of weird. It starts to jitter a lot, you know? It kind of starts to jitter. So if I make it like 100, you will see what I mean. Right. Yeah, so it explodes. it's so stiff, the inner pressure just exploded the entire rope yet again. Right, you can look at that one more time. So it's just like that's how it just fucking explodes. All right, so let's actually keep it around like maybe 20. I think that's gonna be all right. Okay, that's pretty poog. You know what's kind of cool? We can actually color the nodes with the same color as the connections. Who said we can't do that? I think we can. All right. Okay. And we also can make the size of the nodes equal to 30. Okay, so I think we can just divide it by 2. And this is literally a rope, actually. So, kind of. It even looks like a rope. No? That's pretty cool. Isn't it? I think it's a rope. Looks like a snake. Yeah. Roping around here. Okay, let's actually go back. Okay. I'm actually surprised that this idea works. Like, I know nothing about like physics or anything like that, so I think this thing even jitters. Oh, I know why. I think when we're dragging a thing around, we should not recompute the velocity of this thing. Right. So let me... Actually, when we're doing the velocity, we can do the following thing. If it not equal drag, only then apply the velocity to the current rope. So the thing that you're currently dragging, don't try to mess with its position. So basically disable the velocity for this thing. Right, so that's what we can do in here. And that way, as you can see, it doesn't jitter when we actually you know, dragging it around, because you know its position is not updated according to its velocity. That's kind of cool. Okay. That's kind of cool. So I think we basically fixed what I wanted to fix initially. So now we can drag it however we want. So the next step is going to be actually have several connections to the same node. So have some sort of a tree or maybe even a graph. Right, we'll see. So, okay, allow to drag any node. And I'm gonna push that right into the repo. Okay, so I think before I go and implement sort of like a graph rope, is that even a thing, like a graphy rope? But anyway, before I go implement the graph, I think I want to make a small break and make a cup of tea. Yeah, after the break, we're gonna just continue. All right, so let's try to implement the graph rope. And I think it would actually make sense to show an example what I mean by graph rope. I mean something like gorse. Gorse? How do you pronounce that? I'm not sure. Gorse. And this is basically the version control visualizer. And it basically can take your file tree and visualize it like that. And when it's visualizing, it actually acts like ropes, which is kind of cool. I wonder if I can actually demonstrate. So do I have gorse? I do have it. Okay, so we can actually try to do that on something like Olive C. Why not? So let's do gorse. And it's reading the logs. It's reading the logs. And so as you can see, this entire thing acts like sort of a rope, but it also has this like a tree connections and stuff like that. I wonder if I can like speed it up, but it would be, yeah, as you can see, yeah, there we go. So it's starting to have some stuff. So we can try to implement something similar to this, if you know what I mean. Something similar to this. So at some point there should be some sort of explosion when I start to, yeah, there we go. So now we can clearly see that this is a tree. Yeah, so I want to implement something like that. And if you never heard about Gorse, I recommend to check it out. It's actually pretty fun, and especially fun to like test that on your big project at work, right? If you have a big project at work, it's really fun to just see how it was evolving. And they're usually very big, and if you have like a big team, you can see how like each member of the team worked on different stuff. So it's kind of fun. I'm gonna put that in the description for anyone who's interested. So yeah, Gorse. Okay, so I want to implement kind of something like that, right? So when I was talking about like, you know, the graph ropes. So, but here is an interesting thing. How are we going to represent all of that? So if we have like a one-dimensional rope, so this is a two-dimensional rope. Right? If we have like a one-dimensional rope, we could just store that in an array. But, so what if we have branches? So you're already starting to store a graph. And there are different ways to store a graph. So here we don't really have a directional graph. So we have indirectional graph. Or is it like a non-directional graph? I think it's a non-directional graph. So we can have some sort of like adjacency lists or something like that. So that would be rather interesting. Or maybe we can just store the list of edges, at least for now. So it also depends on how we're going to be modifying this graph, right? Because we'll need to build that graph at some point. So what I'm thinking, how we're going to be building that graph. So let me actually go back to this thing. My idea is the following. So at the beginning, I think we should start with a rope with a length 1. Right, so let's actually rebuild it, and there we go. So it doesn't particularly work because subscript out of bounds, and this is an error, and this is a subscript out of bounds, but on top of that I check, really, and this is a compilation error. To be fair, this should be probably a compile time if. This is really interesting. Huh, should this really be a compile time error? Think about it. Should this really be a compile time error? Huh. But you can eliminate the compile time error if you use the compile time if, which will effectively get rid of this entire code. Which kind of makes sense. So the language kind of forces you to... I don't know what to make out of that. I mean, it's okay, I guess. It's just interesting to think about, you know what I mean? It's kind of interesting. Right. So in essentially, what I was saying. So we're gonna start with just a single node, and what we're gonna do, we're gonna basically add nodes by clicking on them, right? So when I click on this thing, it should create a new node connected to this one, and then another one, and then another one, and then another one. So, and if you have several of them, right? So if you have something like, let's say 3, all these things, right? By clicking somewhere in the middle, you basically branch out this entire thing. So this is how we're going to be building the rope. Right. So because this is the easiest way to implement it. So I'm not really sure if it's going to be just a single click, or maybe you have to hold Control. Maybe that would make sense, right? So you hold Control, you just click that, and it just pops out a new node for you connected to this one. Right. So if we're going to be updating the graph like that, what's going to be the best representation for this entire thing, right? Well, obviously we're going to have some sort of nodes, which is going to be a dynamic array, right? So this is basically how you represent dynamic arrays in Java, in the language, right? So, and it allows you to add things into those dynamic arrays, right? So you basically, what am I doing? Array add nodes, and then you'll be able to add like a new thing in here. And every time you click on something, it makes it super easy to just add another thing in here, right? But then we also need to add additional connections. So what's the easiest way to add additional connection? Well, we can also have an array of segments, right? So segments, and it's probably going to be also this dynamic array. And yeah, a segment is essentially a structure which connects the first one, right, and then the second one, right? So, and they're basically connected together. So, and looking up in this segment list is going to be linear. which I guess fine for such a small project, right? Which is probably fine for such a small project. And on top of that, this thing is non-directional, so this is a non-directional graph. So if you have duplicates in here, is that fine? Probably fine as well. Probably fine as well. Or we can have dynamic array of dynamic arrays of integers. That makes sense, I suppose, right? Yeah, that makes sense in my opinion. Yeah, dynamic array of dynamic arrays of integers, and in the corresponding index, you have a list of index of the connections. So I think that's a pretty good way of thinking about that. I think it is. Okay, that's pretty cool. And I suppose, so this is just a rope, and I think I'm gonna start with renaming rope into knots, I think. Let's query replace rope knots. So what's interesting is that I think rope length doesn't make any sense anymore, right? So this is going to be just knots. So then also have knots velocity. So this is knots. And I'm just thinking. Yeah. Knots velocity. I can't see what's behind this thing. So that's definitely going to be replaced. Rope length should go away, that's for sure. It should just go away at some point. But the question is how we're going to replace that. We're going to have several arrays, right? So this thing becomes a dynamic array, as well as velocities, right? Everything becomes a dynamic array, so everything is dynamic array. And I suppose in here we can just add a single knot, right? So it's going to be array add knots, and the thing we add in here is probably make velocity, and we're going to be somewhere. Let's actually put it at the center of the window, right? So this is going to be width, maybe window width divided by 2, window height divided by 2, right? And there we go. So we're going to start with a single knot at the center. Then what's interesting is that every time we add this sort of knot, we need to add the things to the all of the parallel arrays, which kind of makes sense. Maybe we should make an array of structures. So we have basically arrays of structures. Maybe we have, yeah. So we have a bunch of parallel arrays. So I think maybe we should create just a structure for now, right? So because it's going to be like easier for me to manage, if you know what I mean. Right, so here we can have position, right? So this is the position, vector 2. Then we're gonna have velocity, vector 2 as well, and the neighbors, which is a dynamic array of integers, right? And that way we can just reduce all of that to that. So that kind of makes sense. And we can as well create a thing, something like, can I actually just do something like not and define only position? Is that something I can do? I don't remember. So make vector. So as far as now I can use non-constant expressions within the structure literals these days, so that should be fine. Maybe, I don't know. We'll see. The compiler will always tell us, right? If something is wrong, the compiler will always tell us. That's the beauty of the statically typed compiled languages. Okay. And I hope the rest of the things are going to be zero initialized. So, but we'll see how it goes. I'm not sure if this semicolon is actually needed here. Okay, let's go to the compilation errors. This has to be a semicolon, of course. Thank you so much, compiler. Procedure call did not match any of the possible... Oh yeah, I know. Thank you very much. So this has to be wrapped like that. And then we're gonna say, please implicitly convert it to whatever is needed to convert this thing. Okay, so what else do we have in here? Okay, that's cool. So that means this idea kind of works. I wonder if I can make it a little bit prettier. Like, so look at that beauty. I wonder if I even have to provide the name of the structure in here. Because look, the compiler might know the name of the structure from the type of this array. So maybe it can infer this entire name. Let's actually find out. And it did. Can your Haskell do that? I mean, it's probably can. But yeah, anyway. And let me continue. Let me continue. So let's actually go through the rest of the compilation errors, right? So we're doing compiler assisted refactoring, and here we iterate in nodes, right? We're going to be comparing it with these sort of positions, right? And then we just put this thing in here. Okay, so then in here we always set the position like so. Anything else? Okay, so rope length. This one is interesting. So now we need to replace rope. We already got rid of it. We need to replace rope length with knots count, right? That's basically what we're doing actually. Okay. All right. So and this becomes oh, and knots velocity. Now it's a part of this entire thing. Okay. Knots velocity. This is a little bit complicated because we have to query replace with regular expression, right? So let's actually do it like that. So we're gonna put this in an entire thing like so, right? And we need to do knots 1 velocity. I think, well, that was rather weird. Let's try to do that. What I can't see. So this, I'm pretty sure this has to be digits, or not necessarily. Actually, I wonder why it simply didn't work. What exactly do I have to put in here? Do you want me to put a question mark? Yeah, I think it wanted me to put a question mark. Yeah, there we go. So now we're talking. Yeah, there we go. So that's what I wanted. Thank you very much. So we have a type mismatch. Right, compute knot velocity. Okay, and when we compute in the knot velocity, we're actually accepting the positions. So we just need to put the positions in here. Right, so we're doing a little bit of the refactoring, but once we're done with the refactoring, I think it's gonna be kind of cool. There we go. Okay. Incompatible, so this is another place where we have to put position. What else do we need to put in here? Okay, so here is the position. Makes sense. Another place. So just a second. Another place for the position. Okay, so finally, okay, cool. So, and it seems to be still working, right? It seems to be still working, but now we have a different representation of the rope, right? We have an array, and the connections are described with these neighbor things. All right. And it's gonna be interesting. So we need to basically, if we need to basically we need to now re-implement compute knot velocity to use the new representation, right? So here we should provide the knot for which we're computing, and instead of neighbors, well, we don't have to provide the neighbor. So we have to actually accept the not, right? And we need to accept the graph itself, right? So this has to be the graph, which is going to be the pointer to the nodes, but maybe it doesn't have to be the pointer because it's an array, right? It's a slice. And that should compute velocity. But since we're accepting this thing by a pointer, we're computing the velocity for that specific node, right? So maybe we should not return anything, right? So we basically ask recompute the node velocity, and it will just do that. And then we'll just have to go through each individual node and just recompute its velocity, and we don't have to think about, oh, how many neighbors does it have, or stuff like that. We don't have to worry about that. So here we can quite easily to actually do not neighbors. Furthermore, we can do a pretty cool thing. We can do using, which actually imports all of the internals of the node into the current space. Which means when we refer to neighbors, we refer to neighbors of this one. So this becomes sort of like a method of the node, right? Which is kind of cool, I think. Right. So here, so this is the neighbors, and when we're referring to node, we're referring to the position of the current thing, and it is an index of the neighbors. So that means we have to do graph it position. So let's actually go through the compilation errors maybe. Okay, so this one has to be the position, and this one is the graph. Might as well do something like neighbor, the current neighbor, which is graph it pointer, right? And that way I can just do neighbor position, right? And in here we can also do neighbor position, and target. So this is the position, right? And this is, well, this one is, I think this is the neighbor position then. Neighbor position. And not is the position. I feel like I might fuck up something in here. And result is very interesting. Result is basically the final velocity that we're going to have. So I think I'm gonna just set the current velocity to 0, and then I'm gonna be incrementing the velocity like so, and I don't have to return anything. So let me see. Okay. So when we recompute the velocity, right, so this is the node velocity, I might just provide the current thing. Oh yeah, this time I just can do nodes. I'm gonna iterate them by the pointer, right, I'm iterating them by the pointer, and then compute node velocity is just it, and then also provide the nodes. So, and that should be it. So this is the entire recomputation, right? So this is how we recompute all of these things. Right, recompute all of the velocities in here. So then we're updating all of that stuff. So I'm thinking, since we're computing all of that, maybe we can update the positions of these things also right away. So we can do it position plus it velocity multiplied by the current delta time. So yeah, it actually simplifies all of that, so that's pretty cool. That is pretty cool. So another problem we might have is with how we connect things, right? Because we have like a non-directional graph, right? Doesn't have any direction. And one of the things we're probably going to be doing is duplicating the connection between those things. You know what? I think I'm gonna do the following thing. I'm gonna just iterate all of the nodes, then I'm gonna iterate all of the neighbors, right? And I'm gonna literally duplicate the connections, because why not? I mean, sure. Okay, so, and I'm gonna just do, so this is gonna be, So I can do not. I'm not sure where you have to put this thing in here, so I'm gonna try to put it in here. Right, but we'll see how it goes. And this is the neighbor. Right, so this is the neighbor. I might as well just do something like neighbor, which is not it, and it's gonna be a pointer. Right, sure. So we're drawing the position between the not and the neighbor. Yeah. So we're gonna just duplicate these things. Why not? Because it's too much effort to not duplicate it, and I don't think it's gonna pay off. After that, we need to iterate through all of these things again because we want to draw these circles, right? So this is gonna be not, and it's just gonna be like that. It position, and that's basically it. I think that's it, right? Okay, so this one is not, and this one is not. Okay, so that's cool. Does it work? It's still working. So we don't have a way to create a new node yet, but we can do it right now. Okay, so when I do mouse down, is there any way for me to check if any of the keys are currently pressed, like if the control currently pressed? So let's actually find out. Maybe there is something in the event itself, right? So we can go to module input, right, to module input, and let me find the event. So, okay, so this is event, and there are some modifiers. Okay, I called it, right? So we have modifiers flag, which is a type. Right, and within the modifiers, so essentially it just basically brings the control pressed or alt pressed or something like that. Sure. And I think we can do something interesting in here. If we are unpressing something, and if so we always set the drag to -1, and if you are inside of something, right, if you are inside of something, well, you're always kind of inside of something if you're currently dragging. So we can do something like if drag is equal to 0, so that means you're inside of some certain thing, and it control pressed, we can use this thing to create a new node, right? So what we can do, we can just do array add nodes, right? We're creating a new node. So we can actually create that node somewhere here. So not new node. So the new node position is going to be the position of the mouse, right? So we can just straight up say, okay, so this is the mouse position. Cool. Velocity is probably going to be empty, right? So, well, I mean, maybe I'll have to zero initialize it, so I don't have to worry about that. Not. Velocity, okay, and now in terms of neighbors, right? So what's going to be the neighbor? New not neighbors array add, and we're adding the thing that we're currently dragging, right? The thing that we're currently dragging. And now we have to do the opposite thing. We do nots, the thing that we're dragging, we take the neighbors, right? We take the neighbors, and we're going to add, the count of nodes, which is going to be the new index when we push there a new node, right? So we create a new node, and we do a bidirectional connection right away, right? And that should happen only when you have like control pressed. I think that makes sense. Okay, so let's give it a try, and let's see if it works. So I should be able to just drag it around. When I press control, nothing happened. Okay, cool. So let me see if anything happens. create new node or not. Right. So let's see. Nothing happened. Pogue. It doesn't handle control pressed. That's so cool. Yo, I'm so happy. That's very interesting. Maybe it just simply doesn't handle that. Who knows? This is confusing. Below key pressed means the key was just pressed. Here pressed means the key is held down. Yeah, well, that's true. I can agree with that. Only set for event keyboard. God damn it. Is it event key? Well, I mean, it is event keyboard. So, well, I mean, what's interesting is that mouse button left is on the keyboard event, but it might be not set for X11, right? Well, it's usually set, right? So we can clearly see that it is set. Yeah, so something is clearly wrong in here. Oh boy, where is my soy? Okay, so keys pressed, keys unpressed. Let me see. I just want to see something. Yeah. What about shift? Maybe I can use shift. Maybe shift is going to work. Nah, none of that works. What about using left button? Okay, let's use the left button. Alright, so keys, mouse, button, I mean right, yeah, so I think I said right. Okay, so that's cool. I think if it's not pressed, right, so we unpressed that thing. And we only want to do that if we're inside of something, right? If we are inside of something. Are we inside of something? We're only inside of something. Yeah. So we have to replace drag with it in here. Right. So drag with it, and in here we don't have to do anything anymore. Right. So button right, unpressed, iterate through all the thing, find the closest one, create a new knot. There we go. Create new knot. Cool. Should be fine. Let's go through the compilation errors. So procedure call didn't match any of the overloads, which you didn't like. Mismatch the type, wanted not. Type wanted int, but got not. Okay, so this is because it's it index. Is it it index? Well, can we just use... Well, yeah, here is the it index, but then here we can use it. It's the neighbors of the thing that we're currently iterating. We just put nots in here, and the not, and then we just add the new one. Okay, so I hope I didn't confuse anything here too much. Okay, I can move it around. That's funny. It fucking works. It fucking works exactly as I want it to work. Like, holy shit. Yeah. Yo, what the fuck? Again, it's jittering a little bit when I'm dragging it around. So let's actually do the following thing. Right. If it index not equal to drag, right? Only then we're gonna do that. So I think that's pretty cool. We're gonna start with that, create a new one, a new one, a new one, and then just like drag it around. Does it jitter? It's... no, it doesn't jitter. Okay, so that's fine. That's so fun. Holy shit. So there is another interesting thing about how the Gorse works, right? So there's another interesting thing about how Gorse works, is that all of the neighbors are always trying to spread into the even intervals of the angles, right? So they always, if they're like stick together like that, they always also nudge towards like something like this, if you know what I mean, right? So, but how can we implement that? I'm not sure if if it's gonna be too complicated, but that's kind of cool. Yeah, maybe we can have some sort of a repulsion if those things. Yeah, one of the things we can do, we can just make them to go from each other, right? So if they intersect, they always will try to just go from each other. But that force should be a little bit weaker than the force of the bonds, if you know what I mean, right? So the bonds should be the strongest force. All right, that's kind of cool. I really like that. Boom. So that's cool. All right. Create. Not so. Let's actually remove this entire thing. Okay, so let's actually commit everything we have in here, because I kind of finished what I wanted to do originally. So making them go apart from each other is actually kind of a separate issue that we'll have to address. Okay, implement the rope graph. There we go. I'm gonna push that right into the ribbon. Cool. So compute not velocity. We can try to do that in here, right? We can actually try to do that in here. So here we are iterating all of the neighbors of the current knot. We can as well iterate all of the other things, right? So let's actually call something like other. So I don't remember, where do you put, yeah. So if I want to iterate, I think this is where I keep forgetting. If I iterate by the pointer, yeah, this is where I put it. Okay, so this is a graph, and we are specifically looking for those that are not equal to the current knot. Right, if those things are not equal to the current knot, that's totally fine. So, but we're looking also for position minus other position, and whether they are less or equal to not a radius, right? If this kind of situation has happened, maybe we can even merge these two things. Right, if this situation has happened, we should make them go apart from each other, but since we're computing the velocity specifically for the for this knot, right, specifically for this knot, we probably need to do something like velocity velocity plus so moving towards is going to be other minus knot, moving in an opposite direction is going to be not other. Right, so this is going to be the length, so we need to compute the length. Beautiful bug. So 10 years ago I created this, and this have beautiful bug rotating. Okay, maybe I don't see how it's gonna rotate in this specific case, but sure. Okay, so now I want to have the direction, so I'm going to compute direction in like a similar way. If length is greater than epsilon, then the direction is basically, well, yeah, it's basically this divided by the length. Otherwise, since they're like very much close to each other, we can also pick like arbitrary direction, right? So just to make them follow like yeah, if they're too close to each other, it doesn't really matter, right? You can go in any direction, you're gonna go apart. Anyway, then we can introduce some sort of a parameter, repulsion, right? So this is repulsion. So for now, I'm gonna put it 1 in here, and then we'll see how we can improve that. So, and we basically summarize like all of the velocities, and we'll see how it's gonna go. Okay, so here is, so this has to be if x. Okay, boom. That's cool. They don't go all the way because it's only radius, so it has to be diameter, so we have to multiply it by 2. We can actually multiply it by 3 to have some sort of a padding between them. You know what I mean? But it's actually weird. Like if you have too many of them, maybe there will be no padding. Oh, we'll see. Okay, so I think this is a pretty good solution, right? So you can basically start. That works. That kind of works out, more or less. But repulsion is not strong enough, right? So I think we just need to make the repulsion a bit stronger, like 10, and it might actually work out. Well, yeah. I think 10 is too much, right? But that's kind of cool. That's kind of cool. Okay. Okay, so. They're a little bit jittery. That's kind of the problem in here. They're a bit jittery. Maybe because it doesn't really have to be that big. Maybe repulsion has to be subtle, you know? I think if we just make it a little bit subtle, maybe it might work out actually. But yeah. But maybe it should be on the level of rotation, if you know what I mean. Right. Or maybe we can even make it less than 1, so it's a little bit like even more subtle. Right. So it's just like, it's not like right away, it's just like slowly unsticking. Yeah, I think that works. I think like a little bit more subtle kind of works. So that's a really cool. Isn't that cool? Isn't that cool? So that's really cool, I think. Oh shit. Right. Something exploded in there. Yeah. Okay. Alrighty. So let's actually commit whatever we have. Add a little bit of repulsion between the knots, and I'm gonna push that right into the repo. Alright, so that is basically everything I want you to do for this project, right? So I just want you to play with this specific concept, right, of sort of like the rope, right? So we can actually keep like making the original rope. So this is, okay, so that's really interesting. So there's no way to, oh shit, that would be kind of cool if we could remove certain nodes and then we could split the graph into 2 subgraphs. That would be kind of cool, right? but how can we remove them? So the easiest way to remove them would be by holding Control. But the problem is that Control and Shift just don't work. None of the modifiers work, in fact. So let me see. If I take a look at the module input, right? So flags, and we do using so modifier flags. Let me just go ahead and print something like it modifier flags. I just want to see if like something even happening there, right? Union. Okay, very cool. What I was expecting, how is that a union? It's not a union, is it? Oh, it is a union. It's a structure of U32. Okay, so it is a union, but I can't easily access it as a struct. Oh boy. So, sure. Let's take a look at this stuff. So maybe I can just like literally press those things. And then just do it. So I need to remove this stuff. Print. Boom. Boom. It's kind of dumb, but okay. Sure. Alright. What do we have? So I also forgot the new lines between these things. Let's take a look. I'm pressing Controls, Alts. None of them work. Like, literally none of them work. And I suppose maybe... Okay, so X11 obviously sets Control press. But does it set them... It sets them on key release. But where do we set mouse button? It never sets them on button press, because it doesn't really have that information, does it? Okay, so for instance here, you have key release. So it has this state in here, right? It has this state in here. Shift mask. And then it also uses shift, which is shift pressed. Okay, so it's only handled for the keys, but not for the buttons in here, right, as you can see. But who said we can't really do that? I mean, who said we can't do that? What if I literally just copy-paste this shit? So, this is that. This is a bit weird, but I'm gonna do the following thing, shift pressed. Maybe it works because these are the unions, and some of the like events, they have an intersection between them. So I'm gonna just use the X key directly, and we'll see how it works. Okay. It doesn't work. It literally doesn't work. It doesn't care. Yeah. I was hoping that maybe I can just like do. What was that? What was it? X button. Is it gonna compile? Oh, but we only did that for the for which one? Yeah, we did that for any of them. So okay, that didn't work. Sure. Sure. Let's use the middle button. Okay. So mouse button middle. If we're unpressing, so I want to do that on unpressing. Okay, so this is going to be the wheel. If you press on the wheel, we're going to try to remove this entire thing. Okay. Alright, so we don't have modifiers, but we have way too many buttons on the mouse, so we can just use those. Alright, so we found something. And we want to remove this thing, and that is kind of difficult to do. We can't easily remove a node. So we can probably introduce something like dead, right? So by default it's going to be false, but then it's going to be something else. All right. So, and essentially, what do we want to do? We probably want to mark it as dead and remove all of the neighbor connections. That's what we want to do. We want to mark it as dead and remove all of the neighbor connections. But then that means that we have to find that thing. But is it? Oh man. You know what? I think I'm gonna do the following thing. So we found this the node that we want to remove, and I'm gonna mark it as dead, and that's it. So I'm just marking it as dead. And throughout all of the handling, if we're dealing with a dead node, we're just not gonna take into account its velocity, its position, and we're not gonna render it. So this is basically, if dead is true, we're gonna simply ignore it, and effectively it will disappear. I think that's the easiest way to sort of remove this thing, but that will require to go through all of the code that handles all of those things. You know what I mean? Right. Anyway, so when we press button, so here we always have to check if it not dead. So for nodes, but only if it's not dead, right? Only if it's not dead. If you found a dead one, I'm sorry, you can't do that. All right, so that's fine. So another thing, if it not dead, can't do that with the dead one, sure. So when we're dragging something around, well, I mean, you can't drag the dead one in the first place, so maybe we don't have to check anything in here, so that should be fine. So when we're iterating the nodes, if it's not dead, only then you can try to compute that thing, right? So then we'll also have to go inside of the node velocity computation and check that we're not trying to do those things there as well. If it's not dead, right, only then we try to handle that. This one is even more interesting. If neighbor not dead either, right? So you might be referring to the dead neighbor. Don't do that, right? And another one, if it's not dead here. Okay. So I think we handled everything here properly. So now we need to go into compute node velocity, right? So we only call this thing in here, and we're never gonna call it with the dead anyway, so who cares? Here, if neighbor dead, if not dead, only then, well, I mean, we can do something like if dead, just continue. Just if dead, just continue. Okay. If other not dead, only then we are gonna try to handle it or do something about it. I guess that is it. Right, I guess that is it. So that should effectively handle all that. So this has to be called not. What else do we have? It also has to be called not. Sure, I think we are ready. So we can drag this thing around, we can create more interesting nodes and so on and so forth. So we can have that thing, and also let's create something like this. Right, and now let's say I want to split this graph into two subgraphs. So yeah, that worked out. That's pretty cool. So yeah, it worked out. Isn't that poog? Isn't that poog? I think it's pretty freaking poog. You can't really connect already existing. It would be kind of cool if you could just say that, okay, connect this now. Or like, this one is rather interesting. And now we have like separate things in here, which actually have a little bit of repulsion, but not too much, right? So it's kind of cool. You can play with that. But the way we actually store them in the memory may result in slowly fragmenting the array of nodes. So the data structure that we're using to represent all of that is not particularly efficient for what we're doing, right? Because I initially designed it to not have deletions, but now it has deletions, so I mean, it is what it is. It isn't what it isn't. It's kind of cool. All right, so add an ability to delete the notes. Okay, so I guess that's literally everything I wanted to do about this project. It's a very simple project just to play around with this concept, right? So I guess that is basically it. All right, I guess that's it for today. Thanks everyone who's watching right now. I really appreciate that. So let's raid somebody because we got raided. So I think we should raid somebody back. To give back to the community, to the epic Twitch community of software developers and the game developers. Alright. So, is anyone streaming anything epic today? Life Overflow is streaming software development. Isn't that cool? I think it's pretty freaking cool. So let's raid Life Overflow. Okay. So let's do raid Live Overflow. Okay. Get ready for the raid. I still don't see the thing. It's so slow. I'm trying to mute myself. Twitch, why are you so slow? It's getting slower and slower every time I open it up. Okay, so let's get ready for the raid. Get ready for the raid, boys and girls, and I see you all next time. All right.